So the next thing we have to cover is position, velocity, and acceleration. I wrote it backwards here because I remember it this way easier. It's not important. Anyway, so position is where something is, right? Where something is on the XY plane, where something is, where my car is if I'm driving to school, right? The position of where I am on my way to school. So the position function is what most functions you'll be dealing with are, right? How far did this thing travel in this amount of time is what is the position of this thing. So if you have a position function that goes like this, right? Something is going down and then coming back up. This looks like some kind of parabola, right? X squared something, right? This position function, you can see that the slope is negative, it's going down, it flattens out, and then it goes back up, right? So this position function is mostly one that you're used to dealing with, right? Any function where something happens and there is a dependent and independent variable, most of the time is going to be a position function. Velocity, probably heard this word before, especially if you took physics, right? Velocity means speed, or in this case, slope. So the slope of this position function, this is your derivative function. Your velocity is your derivative function. It's how the slope is changing on your position function. So if you see down here, it's a negative slope, but it's becoming less and less negative, right? It's like, whoa, it's concave up is what it's called. That's not important yet. But it's getting less and less negative as it's going, right? But it is a negative slope. So the velocity function is going to look, and it flattens out around 1, right? So the velocity function is going to look something like this. What does it mean? Like down here, right? It's a negative slope because the velocity is in the negatives, right? This all is a negative slope. It's going downwards, right? And then at 1, it levels out, which is where it flattens out down here. And then it's a positive slope the rest of the way, right? Positive, positive, positive. And it's increasing, right? It's going higher. The acceleration is what this A is over here. And it's the derivative of the velocity. So it's how the slope of the velocity function is changing. If you look here, it's a positive slope. It's not changing at all ever. It's a normal straight line going up. So your acceleration function here is going to be a flat line like up here that's not flat at all, my fault. A flat line up, boom, up at a positive number, right? So what you have to know is that velocity is the function for your derivative of a position, and the acceleration is the derivative of velocity. So it's just deriving it down the line. Start with position, you derive it, you get velocity, you derive it, you get acceleration. The way I remember this is me and my friend, we remembered it as AVP, right? Because that's the order that it's in. It's backwards, but AVP, we know that position goes first, right? So if you know AVP, we know that velocity comes next and then acceleration. Remember that because the op in CSGO, people go AVP. So that's how I remember it. Remember it any way you want, but you have to know that when you derive a position function, you get the velocity, and when you derive the velocity, you get the acceleration. So what's important to know out of these things is that if your velocity is negative, or if your velocity is negative, that means that your derivative of a position function is negative, right? So that means the slope is negative. So if anything down here in your velocity function, for this one specifically, all of this is negative. Even if this is the slope of this line is increasing, it doesn't matter, right? Because this down here is all negative. So the slope of your position function is negative. So if you have a lot of what they like to do a lot in calculus is they have a plane, and they go, a particle is moving along the XY plane at a speed of whatever, right? And if it's a negative slope, that means it's moving left on the plane because it's going down, right? And if your velocity is positive, that means that it's moving right on the plane. Or sometimes they do it on the y-axis, you go up and down. This you're going to see a lot of later, so just keep that in mind now. We'll go more in-depth later. I just want to introduce you to that. And one more thing, something is speeding up if the velocity and acceleration agree with each other and have the same sign. So, for example, we're going to use these 3 graphs again. This original position function here is decreasing, right? It's decreasing, and it's getting less and less and less steep as it's going down, right? It's slowing down. The reason why you can see that is because all down here, this is all negative for the velocity function, and it's positive for the acceleration function, all of this, right? So it's slowing down, it's getting less steep. And then as it comes up here and it starts to increase at 1 and it gets more and more steep going up, and eventually it's going to be really, really steep, is because the velocity function is positive and the acceleration function is positive. So we're going to look at an example of that and then get into more applications. So if we have a table and it looks really nice, really beautiful, looks like this, and this is your velocity function and your acceleration function, and you're trying to find when your position function is speeding up, right? You have your velocity and your acceleration. You have your derivative and your second derivative, right? You're trying to find when it's speeding up. We just said that if the signs of your velocity and acceleration functions are both the same, it's speeding up, and if they're different, it's slowing down. So if we look at the first one, we have 14, we have -5. This is negative, this is positive, right? So this is slowing down. Next, we have +6, +7. This means it's speeding up. This is -6 and 3. So this means it's slowing down. And this is -4 and -8. And even though these are both negative, since they're the same, it means it's speeding. So anytime your velocity and your acceleration are the same, it's speeding up. Anytime they're different, they're slowing down. The numbers, the individual numbers do not matter at all. This could be +8 million. This could be -62, right? As long as one of them is positive and one of them is negative, it's slowing down. And as long as they are both the same side, it could be both positive, both negative, doesn't matter, it's speeding up. Let's look at more applications. So the last just setup concept that you have to learn is that in a function, the total amount traveled is distance, and the distance from the original point is called displacement. So for example, if my house is right here and the ice cream shop is right here, I'll draw a that's tough. Little ice cream cone, right? This is an ice cream cone. This is my house. If I drive to the ice cream cone, to the ice cream shop, and it's 5 miles away, I drove 5 miles. Everyone can agree the distance from my house is 5 miles. If my sister is staying at her friend's house and it's 2 miles away from the ice cream shop, and after I get the ice cream, I buy ice cream for me and her, and I drive to her house 2 miles back, my distance traveled is 7 miles, right? Because I went 5 miles there, 2 miles back. In total, I drove for 7 miles. But my displacement from my house is only 3 miles, because I'm 3 miles away from my house. So this is what we have to know. The distance from the starting point to the end point is called displacement, and the total traveled is called distance. Now we done with setup. Now we could do calculus. Okay, so we have a practice problem up now. It says the position of a particle moving along the x-axis is given by x of t equals 2t cubed plus 4t minus 5 for t is greater than or equal to 0, where x is measured in meters and t is measured in minutes. The first problem that we have here is to find the average rate of change of the particle during the first 3 minutes. So this is pre-calc, this is unit 1, this is unit 2. The formula for this is f of x2 minus f of x1 over x2 minus x1. You guys should know how to do this by now. Our f of 2 is going to be f of 3, and our x1 is going to be f of 0, right? So to do that, we plug 3 into this. We're going to get 2 times 3 cubed plus 4 times 3 minus 5. We simplify this out. 3 cubed is 27 times 2 is 54 plus 4 times 3 is 12 minus 5. We simplify this out, we get 61. If we plug 0 in, we're just going to get -5 because it's all going to be 0. So we have 61 minus -5 over 3 minus 0. And simplify this out more, we'll get 66 over 3. And 66 over 3 is 22. So the average rate of change is 22, can't forget the unit, meters per minute. And so this next problem here is asking find the displacement during the first 3 minutes. So to find the displacement, we just went over it. It's the end value minus the start value, right? Or the y at the end point minus the y at the beginning. So we already found that our y value at 3 is 61, and our y value at 0 is -5. So 61 minus -5 is 66. You can visualize this. It started at -5, it ended at 61. This is 66 units away. So it went 66 meters because our unit is meters. So that's all you do with this. We already did most of the work on this problem up here. So you just had to remember that it was the end point minus the start point. Okay, so up now we have 3 more problems. This is a different type of problem, but it's using the same equation. So the first one is asking for the velocity of the particle when t equals 6. So up here we have the position function, right? It gives you the position of the particle. The velocity, AVP, comes after position. It is the derivative of the position function. So to find the velocity or the speed or the slope, you're going to derive your original function and then plug in the 6 that it's telling you. If we derive this, we get 6t squared plus 4, and the 5 goes away, it's a constant. And then we plug in our t equals 6 over here. So we get 6 times 6 squared plus 4, 6 times 36 plus 4. When we multiply out 6 times 36, we're going to get 216 plus 4. You're going to get meters per minute. So at t equals 6, the exact speed is 220 meters per minute. The acceleration at t equals 6, what is the acceleration? It's the derivative of the velocity function, right? If this is x prime of t, because our original function is x of t, then the acceleration is x double prime of t, right? It's the derivative of the derivative. We just derive this function that we have here, and we get 12t plus 0, right? We just get 12t. So now if we're plugging in 6, 12 times 6 is 72, and that's just it. So our acceleration at the point t equals 6 is 72, and you have to include the unit, which is meters per minute. And since it's the acceleration, it's per minute per minute, because the speed is increasing at 72 meters per minute every minute, right? So it's per minute per minute. You could write meters over minute squared. I just think that that's more boring. I like per minute. I think it sounds funny. So the last problem here is the particle speeding up or slowing down at t equals 6. If we remember, right, if the signs of the acceleration and the velocity are the same, it's increasing in speed or speeding up. And if the signs are different, it is slowing down. So this right here is a positive 72. And this right here is a positive 220. Don't even have to know what the numbers are. Positive number means it is speeding up. On an AP test, on a math test, on the test your teacher gives you, you should write out a sentence and justify it and say, the particle is speeding up. Don't judge my handwriting, I'm writing fast. Because v of t is greater than 0 and a of t is greater than 0. This is just saying the acceleration is positive and the velocity is positive. They're both positive, they agree, whatever. Yeah, I think that's it for this section. We gonna move on.